Good day. Now that we are all here, let's get started.
Hello everyone, today we are going to talk about solution. But first, what comes to your mind when you hear the word solution? Based on the picture shown, how would you describe solution in chemistry? Solution. A solution is a homogeneous mixture of two or more substances. This may exist in any phase. A solution consists of solute and solvent. The main difference between solute and solvent is that the solute is the substance that dissolves in a solvent to produce a homogeneous mixture, while the solvent is the substance in which a solute dissolves to produce a homogeneous mixture. The difference of those two is simply solvent is the dissolving medium, while the solute is the substance that is being dissolved. Next slide, please. Note that the solvent is the substance that is present in the greatest amount. The best example for solvent is water, because at both temperature, water is able to dissolve more salt than the other solvents. Therefore, it has the highest solubility. In addition, because of its high polarity, water is the most common solvent for ionic compounds. The following examples illustrate solvent and solute in other solutions. Air is the homogeneous mixture of gases. Both the solvent and the solute are gases. Sugar syrup is a solution where sugar is dissolved in water using heat. Water is the solvent and the sugar is the solute. The intermolecular forces between solute and solvent particles must be strong enough to compete with these between solute particles and those between solvent particles. Meaning to say, there must be a strong force in order to compete with the particles of solute and solvent. How does a solution form? To form a solution, energy is required to break the bonds between the particles within the solid or liquid. If more energy is released when new bonds are formed between the solid and solvent than is required to break the bonds within the solid and solvent, the reaction is considered exothermic. Next slide, please. Energy changes in solutions. Step 1. Separate particles of the solute from each other. Step 2. Separate particles of the solvent from each other. Step 3. Combine separated solute and solvent particles to make solution. The diagram shows the first two steps wherein breaking is required apart to pure solute and pure solvent, while the third step requires forming the solution through combination of the expanded molecules. Take note that the process solution can either be endo or exothermic. Sodium chloride will not dissolve in nonpolar liquids as the attraction between the ions and the nonpolar solvent will not compensate for the energies required to separate the ions. Why doesn't sodium chloride dissolve in nonpolar solvents such as hexane? The lattice energy of sodium chloride must be overcome to separate sodium and chloride ions and disperse them into solvent. Hexane is nonpolar. Interactions between ions and nonpolar molecules tend to be very weak. Next slide, please. An enthalpy change is approximately equal to the difference between the energy used to break bonds in a chemical reaction and the energy gained by the formation of chemical bonds in the reaction. It simply describes the energy change of a system at constant pressure. Enthalpy change is denoted by H. What factors causes enthalpy? 4 factors that affects the entropy of a chemical system. 1. Change in phase, physical state. 2. Change in temperature. 3. Change in number of particles, especially for gases. 4. Mixing of particles. Next slide, please. Why do endothermic processes occur? In some processes, like the dissolution of ammonium nitrate in water, heat is absorbed, not released. The dissolution is the process where a solute in gaseous Liquid or solid phase dissolves in a solvent to form a solution. Solubility is the maximum concentration of solute that can dissolve in a solvent to a given temperature. Next slide, please. The enthalpy of solution is the heat released or absorbed when a specified amount of solute dissolves in a certain quantity of solvent at a constant pressure. Entropy is a measure of the randomness or disorder of a system. The value of entropy depends on the mass of a system. It is denoted by the letter S and has units of joules per Kelvin. Entropy can have a positive or negative value. According to the second law of thermodynamics, the entropy of a system can only decrease if the entropy of another system increases. So even though enthalpy may increase, the overall energy of the system can still decrease if the system becomes more disordered. Thank you.
Good day everyone, I am Miss Angel V. Gamiao and I am here to discuss the types of solution. As Miss Mantala said earlier, a solution is a homogeneous mixture of two or more compounds in relative proportions that can be changed continuously up to the solubility limit. The term solution is more frequently associated to the liquid state of matter. However, gases and solids can also form solution. There are different types of solutions that can be classified on a different basis, like the difference in the solute and solvent, number of criteria, and more. It is classified into 4 different bases. The type of solutions on the basis of water as solvent, on the basis of an amount of solvent added, on the basis of the amount of concentration of solute into solutions, and type of solutions on the basis of amount of solute added. But today, we are going to focus on the 3 types of solutions on the basis of the amount of solute added. The first type is the unsaturated solution. Can you please read the definition given under the unsaturated solution, Ms. Sadicon?
Unsaturated, a solution in which the solute completely dissolves.
So, if the solution can still dissolve more solute in solvent, then it is said to be the unsaturated solution. Vinegar is an example of an unsaturated solution of acetic acid in water. The next one is the saturated solution. Can you please read the definition given under the saturated solution, Mr. Quistorio?
Saturated, a solution in which no more solute can dissolve.
So, a solution is said to be saturated only if it reaches its limit to dissolve any more solute in the solvent at a definite temperature. One example of this solution is seawater. Seawater is already saturated with salt. Adding salt forms solid salt crystals instead of dissolving them. And the last one is the supersaturated solution. Can you please read the definition given under the supersaturated solution, Ms. Mantala?
Supersaturated, a solution that contains more solute than a saturated solution.
The solution in which solute is present in an excess amount and is dissolved in the solvent forcefully by raising the temperature is called the supersaturated solution. These excess solute particles are later found in the form of crystals with the help of the crystallization process. Water is a common solvent of supersaturated solutions since it can be heated safely. Next slide po. If the molecule or ion happens to collide with the surface of a particle of the undissolved solute, it may adhere to the particle in a process called crystallization. Although the terms precipitation and crystallization are both used to describe the separation of solid solute from a solution, crystallization refers to the formation of a solid with a well-defined crystalline structure, whereas precipitation refers to the formation of any solid phase, often one with very small particles. Next. Let us proceed to the saturated solutions and solubility. In Figure A, when a solid is added to a solvent in which it is soluble, solute particles leave the surface of the solid and become solvated by the solvent, initially forming an unsaturated solution. While in the figure B, when the maximum possible amount of solute has dissolved, the solution becomes saturated. If excess solute is present, the rate at which solute particles leave the surface of the liquid equals the rate at which they return to the surface of the solid. In figure C, a supersaturated solution can usually be formed from a saturated solution by filtering off the excess solute and lowering the temperature. When a seed crystal of solute is added to a supersaturated solution, solute particles leave solution and form a crystalline precipitate. Various changes can happen if you add more solute to a solution. On a below saturation solution, solvent is not yet holding the maximum amount of the solute it can at that temperature. But if you add more solute to an unsaturated solution, more solute could still dissolve, and if you add more, it will mix in. At the saturation point of a solution, solvent is holding the maximum amount of solute it can at that temperature. If you add any more solute to a saturated solution, it will not dissolve, but it will fall to the bottom that causes precipitation. On a beyond saturation solution, solvent is holding more solute than it is able to at that temperature. Thus, the situation is unstable. If you add anything to the supersaturated solution, the excess solute will crystallize out. Dissolution and crystallization continue as long as excess solid is present. That is all for the types of solution. The next lesson will be discussed by Ms. Sadicon. Thank you.
Good afternoon and welcome to my presentation. As you can see on the screen, our topic is about gases in solution, but first, let's talk about the definition of solution. As Ms. Gamiao and Ms. Mantala said earlier, a solution is a homogeneous mixture of two or more compounds in relative proportions that can be changed continuously up to the solubility limit. For example, air is a mixture of oxygen and nitrogen with trace amount of a number of other gases, whereas brass is a mixture of copper and zinc. Also, when we add sugar to the water, you form homogeneous mixture called solution. Next slide, please. So now, let's talk about the two components of solution, which is solvent and solute, but first, let's talk about solvent. Solvent is the component of solution that is present in the largest amount, is called a solvent. It's the liquid that the solute is dissolved in. A solvent is usually a liquid. It can, however, be a gas, a solid, or a supercritical fluid. Temperature and the presence of other compounds in a simple influence the amount of solvent required to dissolve a solute. The word solvent is derived from the Latin word solvo, which meaning to loosen or untie. Solute, a component of a solution that is usually present in trace amounts. The substance that is dissolved in a solution is known as a solute. The solvent is present in higher amounts than the solute in fluid solutions. Concentration is the ratio of the amount of solute in a chemical solution of the amount of solvent present. The example here is salt in water. A solute is usually a solid that dissolves in a liquid. Salt in water is a common example of a solute. The solute, salt, dissolves in the solvent, water, to generate a saline solution. Next slide. Now, let's talk about the 9 types of solutions. Next slide. First is the liquid solutions. The liquid in solution is usually referred to as the solvent, and the substance added as the solute. When both components are liquids, the distinction is lost. The one with the lower concentration is likely to be referred to as the solute. Any component's concentration is a solution can be stated in either weight or volume units. Liquid gas. The example of the solving liquid and gas is cloud and fog. We know that cloud are water vapors in air. Liquid. Secondly, the example of liquid and liquid solution is the solving alcohol and water. Liquid and solid. The example here is jams and butter. So keep in mind that clouds and fog are solution in which liquid is dissolved in gas, while alcohol and water in a solution in which liquid is dissolved in liquid, and jams and butter are solution in which liquid is dissolved in solid. Remember that in all these three solutions, liquid is taken as a solute. Next slide, please. Now, let's talk about the three different types of solid solutions. Solid solutions. A solid solution is a one or more solid state solution in a solvent when the crystal structure of the solvent is not altered by the addition of the solutes and the combination stays in a single homogeneous base. It is referred to as a solution rather than a compound. Solid and gas. The example of solid and gas solutions is smoke. We know that smokes contain carbon particles in air. Solid and liquid. Salt and water are example of solid and liquid solutions. If you've ever gargled with warm salt water to relieve a sore throat, you've made a solution by dissolving salt in water. Solid and solid. Thirdly, the example here is alloy. We know that alloy is made up of two or more metals like copper and tin. Smoke is a solution in which solid is dissolved in gas, while salt and water is a solution for solid and liquid, and alloy is a solution in which solid is dissolved in solid. Next slide, please. Now, let's talk about the three different solutions of gases. Gaseous solutions. A gas solution might be a gas that has been dissolved in a gas, a liquid that has been dissolved in a gas, or a solid that has been dissolved in a gas. They all finished up in the gaseous phase, which is the one thing they share in common. A good example of a gas solution is the air we breathe. Gas and gas. The example of gas and gas solution is air. We know that air is a homogeneous mixture of different gases like nitrogen gas, oxygen gas, noble gases, and so on. Gas and liquid. The example of gas and liquid solution is carbonated drinks. In the carbonated drinks, carbon dioxide is dissolved in water. Gas and solid. Hydrogen gas by platinum is an example of gas in solid. Thank you.
Good day everyone, I am George and Quistorio, and today we will discuss about Lesson 4, Ways of Expressing Concentration of Solution. There are many ways to express concentration mathematically, such as mass percentage, mole fraction, molarity, and molality. Next po. Before we proceed to the topic, let me recap again what is solute and solvent. Solute is substance that dissolved in solvent to form solution, while solvent is a substance that dissolved particles of solute to form solution, meaning solute plus solvent is equal to solution. Like Ms. Sadicon said, the common example of this is salt and water. If the salt combined to water, the salt will dissolve, meaning solute is the salt while solvent is the water. Mass percentage. Mass percentage is one way of representing the concentration of an element in a compound or a component in a mixture. Mass percent of A is equal to mass of a solution over total mass X of solution times 100. Parts per million and parts per billion are units used in atmospheric chemistry to describe the concentration of gases. Parts per million or ppm is equal to mass of a solution over total mass X of solution times 10 raised to 6. Parts per billion or ppb is equal to mass of solution over total mass X of solution times 10 raised to 9. Next po. Example. The solution is made by dissolving 13.5 grams glucose or C6H12O6 in 0.100 kg of water. What is the mass percentage of solute in the solution? Since we are finding the mass percentage of solute, we will use the solution or formula of mass percentage. mass percent of glucose is equal to mass of a glucose over mass of solution times 100. First, identify the given or the given parameters, then substitute it the formula. It will become 13.5 grams over 13.5 grams plus 100 grams times 100. 13.5 grams plus 100 grams is equal to 113.5 grams. If we divide 13.5 grams to 113.5 grams, the answer will be 0.119. In order to convert it to percentage, we will multiply it to 100. Then the final answer will be 11.9%. Next po. Mole fraction. The molar fraction can be represented as X. If the solution consists of A components, A and B, then the solution is mole fraction of solute is equal to moles of solute over moles of solute plus mole of solvent. Or it is equal to mole sub A over mole sub A plus mole sub B. Mole fraction of solvent is equal to moles of solvent over moles of solute plus mole of solvent, or is equal to mole sub B over mole sub A plus mole sub B. Therefore, the sum of the mole fraction of all the components is always equal to 1. Next po. Example, a tank is charged with a mixture of 1 times 10 cube mole of oxygen and 4.5 times 10 cube mole of helium. Calculate the mole fraction of each gas in the mixture. The first thing to do is identify the given parameters given in the problem. Then, identify what is solute and solvent. In the given problem, the solute is helium while the solvent is oxygen. The given parameters are N sub helium is equal to 4.5 times 10 cube mole, and oxygen is equal to 1 times 10 cube mole. Next po. Solution. Mole fraction can be calculated as mole fraction of helium is equal to 4.5 times 10 cube mole over the quantity of 4.5 times 10 cube mole plus quantity plus the quantity of 1 times 10 cube mole plus quantity. First, cancel 10 cube and add 4.5 plus 1. It will become 4.5 mole over 5.5 mole. 4.5 mole over 5.5 mole is equal to 0.82. Mole fraction of oxygen is equal to 1 times 10 cube mole over the quantity of 4.5 times 10 cube mole plus quantity plus the quantity of 1 times 10 cube mole plus quantity. Cancel again the 10 cube mole, then add 4.5 to 1. It will become 1 over 5.5 and divide it will become 0.18. Now, we are done to mass percentage and mole fraction. The two last ways to express concentration, which is molarity and molality, will be discussed by Mr. Magsumbol. Thank you.
Good day everyone. I will be continuing the ways of expressing concentration of solution. So, majority of reaction happen in solution. So it is important to understand how the amount of substance is expressed when it is present in the solution. There are many ways in which the amount of substance in solution is expressed, like molarity, molality, and mole fraction. So what is molarity, molality, and mole fraction? Molarity is the ratio of solvent's moles to a solution total liters. Both of the solute and solvent are part of the solution. Molality, on the other hand, is the ratio of the solute moles to the solvent kilograms. Mole fraction is the mole of a constituent divided by the total mole of constituent in a mixture. Three of them are measures of the concentration of a chemical solution. But most of the time, it doesn't matter which unit of concentration you use. However, molality is preferred when a solution will undergo temperature changes, because altering temperature affects the volume, thus changing concentration if molarity is used. Next slide. Molarity and molality. Molarity is one of the most widely used unit of concentration, and it is denoted by capital letter M. It is defined as number of moles of solute present in 1 liter of solution. Thus, molarity is equal to the number of moles of solution over the volume of solution in liters. Molarity is defined as the moles of solute present in 1 kilogram of solvent. It is denoted by lowercase letter m. Molality, or lowercase m, is equal to the number of moles of solution over the volume of solution in kilogram. Next. Mass percent or weight percent. It is the ratio of the mass of solute to the mass of solution, multiplied by 100 to calculate mass percent. It is also known as the weight percent, and it is represented by weight percent. Mass percent is equal to mass of solute over the mass of solution times 100. Next na. Mole fraction. Next. The mole fraction or molar fraction is defined as the amount of constituent divided by the total amount of constituent in a mixture. So the formula is the molar fraction is equal to any given amount of constituent over the total amount of constituent in mixture. The sum of the mole fraction is equal to 1. So basically, the formula means that the summation of all mole fraction is equal to 1. The formula is just a way to express it in a symbol and number so that we can have a better picture on how it happened. Because it is a ratio, mole fraction is unitless expression. The mole fraction of all components of solution, when added together, this is equal to 1. Next slide. Let's have an indicative example of molarity. So the question is, how much water should be added to 1 liter of 1 mole potassium hydroxide solution to make it 0.2 mole potassium hydroxide solution? So let's use the molarity formula, which is number of moles of solution over the volume of solution in liters. Now we know that 0.2 over 1x, then we will change this based from the formula, so it will become x is equal to 1 over 0.2. Then we will divide it to get the answer 5. So extra 4 liters of water should be added to 1 liter of 1 mole potassium hydroxide to make it 0.2 mole potassium hydroxide solution.
Good day, everyone. I am here to tackle about Lesson 5, the factors affecting solubility. Next slide, please. Solute-solvent interaction is the interactions between solvents and their solutes are widely regarded as one of the most important topics in organic chemistry and are central in controlling solubility, reactivity, and structure. Next slide, please. Chemists use the axiom like dissolves like. Polar substances tend to dissolve in polar solvents. Non-polar substances tend to dissolve in non-polar solvent. So, like dissolves likes means if any substance is polar, then polar and ionic substances will be dissolved in it. Example is the HCl in water. If the solvent is non-polar, then the non-polar substances only can be dissolved in it. Example is the hexane in benzene. Next slide, please. The question here is, will all solvents dissolve all solutes? So to answer the question, it is no. Generally, both solvents and solutes are separated into two types, the polar ionic and non-polar.
The rule of thumb is that like dissolves like, polar ionic solvents dissolve polar ionic solutes, and nonpolar solvents dissolve nonpolar solutes. For example, water is a polar solvent, and it will dissolve salts and other polar molecules but not nonpolar molecules like oil. Petrol is a nonpolar solvent and will dissolve oil but will not mix with water. Next slide, please. The more similar the intermolecular attractions, the more likely one substance is to be soluble in another. On the screen, as you can see, it is a hydrogen bond. Hydrogen bonding and aqueous solubility. So the example here is the cyclohexane. C6H12 has no polar OH groups, and cyclohexane is essentially insoluble in water, and glucose C6H12 O6 has 5 OH groups. Glucose is highly soluble in water. The hydroxyl groups in glucose molecules can form strong hydrogen bonds with the solvent water molecules, so glucose is soluble in water. In contrast, cyclohexane is not capable of forming strong intermolecular attractions with water. So the water cyclohexane interactions are not as energetically favorable as the interactions that already exist among polar water molecules, or glucose is polar and cyclohexane is nonpolar. Polar solutes are generally soluble in polar solvents such as water, and nonpolar solutes such as cyclohexane are not soluble in the polar solvent. Next, Beth. Vitamin A is soluble in nonpolar compounds. Vitamin C is soluble in water. So, vitamin C is soluble in water because it has many opportunities to form hydrogen bonds and dipole-dipole interactions with solvent and solvent water molecules. Vitamin C does not dissolve in nonpolar solvents like hydrocarbons or fats. Vitamin C is said to be insoluble in nonpolar solvents, while vitamin A, also known as retinol, is nonpolar and can dissolve in fat in your body because fat is also a nonpolar substance. Next slide. As you can see on the screen, it is a table of solubilities of some alcohols in water and hexane. So we have here the alcohol that is soluble in water and soluble in hexane. So the infinity sign means that it indicates that the alcohol is completely miscible with the solvent. So methanol is miscible in water while it is 0.12 in hexane. Next one is the ethanol. Ethanol is miscible with water and hexane. Next one is the propanol. Propanol is miscible also with water and hexane. Next one is the butanol. Butanol is 0.11 soluble in water and miscible with hexane. Next one is the pentanol. Pentanol is 0.030 soluble in water while it is miscible with hexane. Next one is the hexanol. Hexanol is 0.0058 soluble in water and miscible with hexane. The last one is the heptanol, which is 0.008 soluble with water and miscible with hexane. That's all. Thank you.
I am Christian Dave Mercene Domingo, and tonight I will tackle the colligative properties of non-electrolyte and electrolyte solutions. Next slide. Colligative properties. Colligative properties are physical properties of a solution that depends on the amount of a solute, but not on the nature of solute. This means similar amounts of completely different solutes can alter these physical properties in similar quantities. Hence, the colligative properties depend on the ratio of the solute amount and solvent amount. For a given solute-solvent mass ratio, all colligative properties are inversely proportional to solute molar mass. Electrolytes are substances that can form solutions that are able to conduct electricity through this solution. Such solutions are known as electrolytic solutions. Non-electrolytes are substances that are not capable of forming electrolytic solutions. Both these types, electrolytes and non-electrolytes, have colligative properties. There are four major colligative properties: freezing point depression, boiling point elevation, osmotic pressure, and vapor pressure lowering. Four major colligative properties. The first one is the freezing point depression. Freezing point depression is the phenomena that describes why adding a solute to a solvent results in the lowering of the freezing point of the solvent. When a substance starts to freeze, the molecules slow down due to the decrease in temperature, and the intermolecular forces start to take over. The second colligative property is the boiling point elevation. The boiling point of a solvent will increase when a solute is dissolved in it. This is referred to as boiling point elevation. The elevation of the boiling point is directly dependent on the amount of solute present in the solution, but it is not based on the identity of the solute, so it is considered a colligative property. The third colligative property is osmotic pressure. It is a colligative property of solutions that is observed using a semi-permeable membrane, a barrier with pores small enough to allow the solvent molecules to pass through but not solute molecules or ions. Fourth is the vapor pressure lowering. The vapor pressure of a solvent in a solution is always lower than the vapor pressure of the pure solvent. The vapor pressure lowering is directly proportional to the mole fraction of the solute. Next slide. Colligative properties of electrolytes are the physical properties of electrolytic solutions that depend on the amount of solutes regardless the nature of solutes. The solutes present in electrolytic solutions are atoms, molecules, or ions having either lost or gained electrons to become electrically conductive. When an electrolyte is dissolved in a solvent such as water or H2O, the electrolyte separates into ions or any other conductive species. Therefore, dissolving 1 mole of electrolyte always yields 2 or more moles of conductive species. Hence, the colligative properties of the electrolytes are considerably changing when an electrolyte is dissolved in a solvent. Next slide. Colligative electrolytes is the amount of solutes regardless the nature of solutes. Non-electrolytes are substances that do not create conductive solutions when dissolved in a solvent. For example, sugar is a non-electrolyte because when sugar is dissolved in water, it exists in molecular form, does not dissociate into ions. The sugar molecules are incapable of conducting electric currents through the solution. The number of solutes present in a non-electrolytic solution is less compared to an electrolytic solution. Therefore, the effect of non-electrolytes on colligative properties is also very low. For example, the degree of vapor pressure lowering by adding sodium chloride or NaCl is higher compared to the addition of sugar to a similar solution. Next slide. Electrolytes provide more solutes to the solution via dissociation. Hence, the colligative properties are considerably changed. While on the other hand, non-electrolytes provide low solute to the solution since there is no dissociation. Hence, the colligative properties are not considerably changed. Next slide. In conclusion, the effect of electrolytes on colligative properties is very high compared to non-electrolytes.